Okay, it's time for the equilibrium lab, and the equilibrium lab and the buffers lab, the last two labs, are pretty intense. They're intense experimentally, and they're intense, well, actually, buffers isn't intense experimentally, but equilibrium this is a tough lab to do experimentally. It is a tough lab to analyze. Buffers is a very tough lab to analyze. So we're going to be building on a lot of the stuff you're learning in class. And good news is, if you can learn these labs, sometimes by having your hands-on appreciation of it, you really helps to reinforce what you're learning in class and helps make sense of stuff that seems to be just pure math. Hopefully now you get a sense of it. So there's a lot of stuff going on in here. First, a new thing is that we are going to mix reactants together to make a reaction mixture. But when you mix them together, you're ending up diluting them, right? So I started with 3 milliliters of a solution, but I then add 3 milliliters of the second reactant. Well, now I've kind of effectively diluted it. So we have to learn how to adjust our dilution equations for these reaction mixtures. We need to be able to calculate equilibrium concentration of a reactant mixture using colorimetry. Now this is just a repeat of what we did in lab 1 and lab 3, so that's not particularly bad. Then we're going to introduce this ICE algebra, initial change equilibrium, and stoichiometry to be able to find these equilibrium concentrations, and then to be able to use all the balanced chemical equation to figure out what all the other equilibrium concentrations have to be. You'll have a lot of trouble with that. I'll help you. How to write a K expression from a balanced chemical reaction, how to calculate the value of K once we have equilibrium concentrations, and the big concept, which gets lost in the message because we're doing so much math, is that an equilibrium constant is a constant. It doesn't change. It doesn't matter what your initial concentrations are. It doesn't even matter what your your equilibrium concentrations are. The ratio is going to be a fixed constant. That's the idea of an equilibrium constant. And it's only going to change if your temperature changes. So if you do all of your reactions at the same temperature, we should get the same equilibrium constant regardless of the initial conditions. Let's see. All right, what you hopefully should know, but you don't because you're just starting to do this in class. So some of this you've learned, some of this is just new information. Every reaction is reversible, at least slightly. That means that while reactants can react and form products, also the products can react backwards and form the reactants. So it's, there's just both things are happening, which means that this idea that I put some reactants in a beaker and then magically, poof, it's all turned to products is not realistic. It turns out many equations for many chemical reactions, that forward reaction is so much more favorable than the reverse reaction, that for all practical purposes, that's close enough to true anyways that that's fine. But in these chapters, we're going to be dealing with reactions where that's not true. So what happens is that it appears to stop. I mix them, and at first everything's reacting, and then all of a sudden it appears to stop. And all the concentrations aren't changing anymore. They haven't actually stopped. What's really happening is the forward reaction is taking reactants and making products, and the backward reaction is taking those products and undoing the reaction and making reactants again. And if they happen at the same rate, if one person's unstacking Legos at the same rate as another person is taking the unstacked labels and restacking them, then the piles appear not to be changing. I'm still having the same amount of unstacked as stacked labels. So we call that the equilibrium point. And at that equilibrium point, it is true that we have an equilibrium constant. And the equilibrium constant is the forward over the reverse rate constants. But more importantly, it's going to be related to the equilibrium concentrations of the reactants and products in there. We'll talk about that expression in a minute. So every reversible reaction has some kind of point at this point where this reaction is stopped and I have a ratio of equilibrium concentrations and it appears to stop. We can measure it, but we can't change it. It just is what it is. So some of them So at equilibrium, the concentrations are no longer changing. But when it first starts, the reactants concentrations are changing. So in other words, it doesn't get to equilibrium right away. At the beginning, I'm having more forward reaction than reverse reaction. So I am changing concentration of my reactants at the beginning of the reaction, but I get to a certain point where they stop changing, and that's when I've reached equilibrium. Now, at equilibrium, these ratio products to reactants doesn't change. This will have a K expression that's a ratio of the concentration of the products to the concentration of the reactants. And at some of them equilibrate with more products than reactants. We might say that that's a product favored reaction, and we would have very large K values for that. And so other reactions equilibrate where very little of the reactant has actually converted out. It's more reactants than products. And those have very small Ks. So like a weak acid, right? Only dissociates slightly. That would be an example of a reaction that equilibrates with mostly reactants. Most of the reactants remain undissociated. That would be a small K value. Okay, so this equilibrium constant. We have to make a new chemical formula for the new equation for this for every reaction, and that's very frustrating. So I can't even write a equation because the equation depends on the chemical reaction, but we can kind of say it in terms. So the concentration, the top of it is the product, meaning I multiply a bunch of numbers together, of the concentration of each product raised to the power of its coefficient. And these are equilibrium concentrations. These are not what we start off with. This is once it's hit that part where the concentration isn't changing. So the equilibrium concentration of each product raised to the power of its coefficient. And then I do, on the denominator, it's the same thing. It's product, but it's all for the reactant. So it's the product of the concentration of each reactant raised to their coefficient powers. So for instance, if I have this reaction, one nitrogen plus 3 hydrogen makes 2 ammonia. And this is not the preferred. Usually we use a half barb arrow going backwards, but sometimes we'll just use double arrows because it works. So I take the product, ammonia, I take the constant equilibrium concentration of it, and I square it because there's 2 of them. That's my numerator. In my denominator, I go to the reactants. So I have the concentration of nitrogen raised to the 1 power. That's what this is. And the concentration of hydrogen cubed because there's 3 of them. If I had a different reaction where I have 2 products and 2 reactants, note that now I have 1 NO and 1 SO3, so I have concentration of NO and concentration of SO3, both are raised to the 1st power because there's 1 of them. And on the bottom I have SO2 and NO2. So, and this is the, we use our brackets for molarity of X. Don't forget, it's the equilibrium, a lot of times we write EQ at the end of here, and that is kind of an important detail. So how do I find the equilibrium constant for a reaction? Once it's known, I can say all sorts of things about the chemical reaction. I can say this is product favored, it's reactant favored, and I can sort of figure out how likely is this reaction, are my products going to be made. And I can also prorate my theoretical yield from stoichiometry to account for the fact that it doesn't go to completion. This is particularly important if you're in a manufacturing plant and it's look, we're trying to sell this product. We're going to need to know what do I need to do to make that favorable, and what should I expect as a realistic yield. But again, we have to have equilibrium concentration of all the products and reactants. So if I measure how much I put on a scale and then how much I dilute it with water, that's not useful. That will tell me what the concentration of a solution that I make is at initially, but I need to know what is it at equilibrium. So I need some kind of analytical tools to be able to say what is to measure concentration in solution. And of course, we have one, that's colorimetry. That's not the only one, but titration would be another one. But I can use that to say, okay, this is the equilibrium concentration. All right, now let's talk about this ICE table, initial change equilibrium. The idea is I can calculate my initial concentrations from some knowledge of the reactant, and if I'm in lab, I can weigh stuff out or pipette it out, and I can record the volumes and everything, so I can figure out initial concentrations. but then some of it reacts. I don't know how much it reacts. If I knew how much it reacts, I wouldn't need to do this. So we usually say some of it reacts by putting a change. So this is my initial concentrations. Note the initial concentration of my products in most cases, unless I've had added them into my mixture, I start with none of them. So they're usually initially 0. My change is then something reacts. Now in this case, this reaction is one of these and one of these makes one of these and one of these. If you look on the past slide. So I would expect 1 or X of SO2 reacts and X moles of NO2 reacts, and they would make X moles of NO and X moles of SO3. If I had coefficients in this reaction, I would have to adjust these X terms by those coefficients. So if this was 2 NO2s, this would be minus 2X because it takes twice as many moles of that. And I noticed that for my reactants, since they're reacting, I'm subtracting X. The change will be I'm going to react some of it. It's going to decrease. But for my products, I'm making it so it's positive. So I get to a point where I said at equilibrium, there is at least a relationship between the initial and the equilibrium concentrations. For every X I make of NO2, I also make X of SO3, and I make 0.5, the initial minus X of SO2 and the initial minus X of NO2. So I can calculate this and then put those into that K expression formula that I created. And I have a messy algebra, but it's a solvable algebra problem. And we can use, Wolfram Alpha, we can use Google, we can use different things to say solve this or factor this, and we can use a quadratic equation. So there's relationships of how you actually solve it, but the point is I could figure stuff out. A lot of times in class you are given the initial concentrations, you calculate the algebraic expressions of the equilibrium concentrations, and I give you K, and you have to tell me stuff about these equilibrium concentrations. In our case, we're going to find K, so I need to actually know what all these are. Somehow I need to figure out what X is. That's where the colorimetry comes in. So let's work an example. What is the equilibrium concentration of the nitrogen oxide gas produced from initial concentrations of 500 milliliters of 0.1 molar SO2 and 500 milliliters of 1 molar NO2? So in this case, K is not tiny, so I can't assume that, in class you'll do these tricks where they say, well, we can assume that X is so small, this is such a small reaction that I can ignore it. I can't do that. So I have my chemical reaction, and I can now do a dilution. Note that I have to take into account that the initial concentration of SO2 and the initial concentration of NO2, even though this doesn't really work because they're gases, but I just kind of put it up there as a concept. When I mixed it, I no longer have 500 milliliters of each. I have 1,000 because it was 500 of each, so I've effectively diluted it. So I need to calculate my concentrations. So it would be 1 molar times half 500 milliliters or half a liter divided by 1 liter total after I mix them together is actually 0.5 molar. Now, in this particular case, because they were identical, I only had to do the concentration once. So that's where I get that 0.5 from. I have to use dilution to figure out from the things that I initially mixed, what are my initial concentrations. And then my products are 0. I don't know how much reacted. Here I get my equilibrium. Now, suppose we measured NO, and I found an equilibrium, I should say NO equilibrium, and it was found to be 0.45 N. So the equilibrium of NO is 0.45 M. That tells me X, right? Since on my table it's X. So if X is 0.45 moles, I can now put X everywhere X is, I can put it in, and now I can actually calculate my equilibrium concentrations. This is effectively what we're going to do in our lab. So in this case, I now have 0.45 of each of the products and 0.05 left of each of the reactants. I can put it into my K expression. Remember, it's the product concentration of the products, since there's only one of each of them, raised to the 1 power, divided by the concentration of the reactants. and I can plug it in, and it turns out I get a K value for this reaction of 81. So it's product favored because it's big, it's bigger than 1. So that means there's more products than there are reactants. I can also see that in this ICE table. So that's how we use ICE tables, and we're going to be using those. Experimentally, we got a couple other tricks going on here. Our job is to find that equilibrium value of iron making iron thiocyanate. So iron ion, iron 3 ion plus thiocyanate ion in an acidic solution will make this iron thiocyanate ion. And it is it's active colorimetrically, so we can use colorimetry to measure the concentration. So our table is going to be whatever our initial concentration of iron is, plus what our initial concentration of thiocyanate ion is. And remember, don't get caught up in the fact that we're not going to use iron 3, right? You can't have an ion by itself. We're using iron 3 nitrate. But once we have it in solution, it dissociates, so it really is iron 3. And the same thing with the thiocyanate. We're going to use sodium thiocyanate. So once I put it into solution, it's really thiocyanate ion and sodium ions. But the sodium ions and the nitrate ions aren't really active in this. They're just kind of sitting around in there. But they are in there. So this would be how I'm going to, this would be the setup of my equilibrium values. We are going to get this equilibrium concentration of the thiocyanate ion by colorimetry. So we're going to first have a standard plot. So we have an equation that relates absorbance and concentration. We're going to measure the absorbance of the reaction mixture, and from that we can calculate what the equilibrium concentration of iron thiocyanate ion is. Then we know X, and we can backfill the table. I told you it was going to be a lot. That's all right. We'll do it together. So again, we're going to relate that concentration to absorbance. We're going to use this proportionality. So that means we have to do a standard curve. We're going to make a calibration curve with 5 known concentrations. Actually, I think it's 4 known concentrations of iron thiocyanate. One is a 0 concentration, and use it. Now, it's a little bit tricky how they get made. I actually have to use the same reaction and drive it to completion. But we really haven't gotten into this idea of how do you drive a reaction to completion, even though that's not favorable. Suffice it to say, if I use very large concentrations of one of the 2 reactants, I can drive it to completion. I'm going to tell you what the concentrations are, which is what makes that so hard. So note that this is in here. I kind of have it explained in case this helps you with some class problems, but you can ignore this. So part A, we have to calibrate our system so that we have this relationship of how does absorbance relate to concentration. So we need to make these solutions fresh. They're not real stable. So we're going to make them. So notice you have to be very careful about this iron nitrate concentration, because in part A we're going to use 0.2 molar. In part B we're going to use 0.05 molar. I think 0.05 or 0.005 molar. So there's 2 different concentrations sitting out. The strong one is going to be for part A, making our standards for our colorimetry. For the reactant mixture in part B, it's going to be the weaker concentration. So to make, this is the concentration of the solution. We've calculated it for you. But it does depend on accurately measuring out this much. So it won't be really what we think it is. So you're going to make these mixtures. Note that there's 3 components in here. You're going to make the, put in the iron nitrate solution, 10 milliliters of that, then 0 milliliters on the first one or half a milliliter on the second one. So you're going to use a volumetric pipette for that. And then when you dilute it, instead of using water to get it up to the line in the volumetric flask, you're going to use 0.3 molar nitric acid. So we're going to dilute it with nitric acid. So you're going to set up the calorimeter, rinse the cuvette with the solution for flask 1. This is going to be considered our blank. And you're going to calibrate it once. Remember, we only hit that cal button once at 430 nanometers. And we're going to say this is the 0 absorbance. It's going to ask you, we're going to set it up so that it asks you what is the concentration. And you're going to type in 0 because that's what's in the first column there. And then we're going to remove it. We're going to do the same thing we did for the kinetics lab. where you dump that solution out, put the new solution in, fill it, dump it out so that you're rinsing the cuvette, put the next one in, put the cuvette in, and just read and record the concentration. So you can use the collect and keep if you want, or you can just write down the concentration, the absorbance values. So when we're done, we're going to measure the absorbance of all 4 solutions. You're going to have a concentration, that's what's here in this table, and then the absorbance. Now you're going to make a curve from that, a calibration curve. You're going to make the plot. You're going to get the line fit of it, and you're going to have your absorbance equals some number times the concentration plus the y-intercept, and that's going to be important for part B. Now, part B, we're going to make equilibrium mixtures. Why these are equilibrium mixtures is because we're going to use this 0.005 molar solution. These are now competitive. They're about similar concentrations. That's going to mean that this is not going to completely form the iron thiocyanate ion. It's only some of it's going to form. We're going to measure how much gets formed. So we're going to make these 4 solutions. These are in a 10 milliliter volumetric. The part A's are in a 25 milliliter volumetric. So we have to make 8 solutions, you notice, and there's a lot of measuring out. If you actually use different volumes than here, record what you actually use. So if you didn't quite get it to 4.50, it's 4.52, record 4.52, because we will calculate what these initial concentrations are. And then you're just going to record the absorbance. So solution 1, absorbance, solution 2, absorbance, solution 3, absorbance, solution 4, absorbance. That is the lab. We're going to clean everything up and finish the lab. That's going to take, not the whole lab probably, but it's going to take a sufficient amount of time. There's a lot of solutions to be made. Once you have all that information, all the analysis is in week 2. But just briefly, because some of this is going to show up on the pre-lab. You're going to have a copy, you're going to have that calibration curve from part A, absorbance and concentration. You get an equation from that. That's going to be the equation that you use to, when you take your absorbance from part B, to convert the absorbance into what is the equilibrium concentration. On that bottom, the equilibrium concentration of the iron thiocyanate ion that we produced. You also need to do some calculations for your initial concentrations. Remember, just like we were talking about with the NO and the SO, we had to dilute them. When we mixed them, they ended up being effectively diluted. So we had to calculate those concentrations. You're going to have to do that. Calculate your initial concentrations for your iron +3 and your thiocyanate ion in that dilution by mixing, and put them in the first row of the ICE table. You're going to use that, your equation from the calorimetry curve to determine the equilibrium concentrations of, we'll have the equilibrium concentrations of the iron thiocyanate, and then from that we can calculate the equilibrium concentrations of the iron 3+ and the iron and the thiocyanate ion. So we fill that out, we figured out X, we write the K expression, and we use the ICE data to calculate the K for each flask. You need to do that on the pre-lab for one of them. You're probably going to need some time and some help, and that's how this is going to look like. So then you're going to do that for all 4 reaction mixtures next week in week 2. I'll see you in lab.